Training and running modern AI models requires an immense amount of electricity. As data center footprints expand, their energy demands are approaching the physical generation limits of our terrestrial power grids. Humanity's total electricity production is dwarfed by our solar system's primary reactor. The sun outputs 3.86 times 10 to the 26th watts of power, more than 100 trillion times our global grid capacity. Historically, engineers proposed capturing this energy through space-based solar power and beaming it back down to Earth via microwaves. However, getting that power efficiently through the atmosphere remains a massive bottleneck. Google's proposal inverts the model. Instead of beaming the power down, the data center infrastructure moves up, permanently relocating AI compute into low Earth orbit. Placing these data centers in a dawn-dusk, sun-synchronous orbit allows them to ride the Terminator line between day and night. This specific trajectory provides near-continuous solar generation, eliminating the downtime of a terrestrial day-night cycle. This plan maps out an 81 satellite cluster utilizing commercial Google Tensor Processing Units, or TPUs. Proving this concept requires meeting specific targets in 4 engineering domains: optical networking, orbital kinematics, radiation hardness, and launch economics. Space-based AI is a multidisciplinary systems engineering optimization problem. In this environment, the physical limits of space dictate the architecture of the computer. Terrestrial TPU pods achieve scale via custom inter-chip interconnects, or ICI, running at hundreds of gigabits per second. Large-scale training workloads require an aggregate bandwidth of roughly 10 terabits per second. But commercial optical intersatellite links, the lasers currently used for satellite communication, max out near 100 gigabits per second. This chart shows achievable bandwidth against distance. Because light beams diverge, received power drops according to the inverse square law. Standard satellite networks operate over thousands of kilometers, which restricts them to the low bandwidth zone in the bottom right. To reach 10 terabits per second, the hardware must operate in the near-field regime. Shrinking the intersatellite distance to under 1.25 kilometers provides enough received power to close the link budget for high spectral efficiency transceivers. Using dense wavelength division multiplexing, the system packs 24 data channels into a single 10-centimeter aperture. At extreme proximity, spatial multiplexing becomes possible. When satellites are within 320 meters, a single aperture supports a 4x4 array of beams, scaling bandwidth inversely with distance. These links require a mechanical pointing accuracy of 1.0 microradian, a precision level already demonstrated by commercial satellite terminals. The physics of optical networking demand a dense, localized cluster. The data center cannot be a loose constellation. It must be a tightly coupled mesh. Maintaining an 81 satellite cluster traveling at orbital velocities is a massive challenge. Constant chemical thrust for station keeping would exhaust fuel supplies almost immediately. Instead, the system uses a free-fall formation. It relies on Keplerian motion to maintain the cluster shape without active propulsion. The cluster follows a specific geometry, a rotating ellipse. In this configuration, the satellites move relative to each other in a way that naturally reproduces the cluster shape once every orbit.
The cluster effectively breathes. The distance between nodes naturally oscillates between 100 and 200 meters twice per orbit, driven by the geometry of their elliptical paths. The primary disruption to this model is the J2 perturbation, a gravitational irregularity caused by the Earth's equatorial bulge. To counter this drift, the cluster's axis ratio is adjusted to exactly 2 to 1.0037. This minor geometric shift reduces J2-related drift to less than 3 meters per second per year. By mapping the orbital mathematics precisely, predictive geometry eliminates the need for heavy chemical station keeping, making a dense optical network sustainable. Hardware in low Earth orbit is exposed to galactic cosmic rays and trapped protons. For a 5-year mission, the baseline exposure is a total ionizing dose of approximately 750 rads. Google tested the V6E Trillium TPU using a 67 mega-electron-volt proton beam, simulating these orbital conditions. The beam pierced the chassis and heat sinks to strike the logic die and memory stacks. The high-bandwidth memory withstood 2,000 rads, nearly triple the dose required for a 5-year lifespan, before showing irregularities. The core logic die proved more resilient, surviving up to 15,000 rads with no permanent hardware failures. Beyond cumulative dose, the system must handle single event effects, instantaneous falls caused by a single energetic particle strike. These strikes cause silent data corruption, where a bit flips in the core logic or SRAM, and the chip continues computing with the wrong value. Tests measured an error rate of 1 per 3 million inferences. While acceptable for inference tasks, long-duration training requires software-level mitigation to catch and correct these bit flips. Commercial silicon is robust enough to survive the LEO environment. The engineering focus shifts from hardware mortality to software-level fault management. The ultimate constraint for any space infrastructure is the cost of lifting mass into orbit. To compare space to ground, we use launched power price, the amortized launch cost per kilowatt of power over the satellite's life. Terrestrial power costs for U.S. data centers range from $570 to $3,000 per kilowatt per year. At current Falcon 9 prices, the space-based equivalent is roughly $14,700 per kilowatt. However, launch pricing has followed a 20% learning curve. For every doubling of mass launched, the price falls. By the mid-2030s, Starship-class vehicles and high component reuse could drive launch costs down to $200 per kilogram. At that $200 mark, the space power cost drops to approximately $810 per kilowatt per year, placing it firmly within the range of terrestrial power spending. Space-based AI economics are directly tied to rocket reusability. Once launch costs cross the parity threshold, the orbital model becomes competitive with terrestrial infrastructure. Terrestrial energy ceilings require a new AI infrastructure. The physics of optical bandwidth dictate a cluster of satellites arranged in a 1-kilometer oscillating freefall lattice. Empirical testing validates that commercial TPU silicon can survive the radiation of this orbital environment. Continuing declines in launch costs close the final gap, making the cluster economically competitive with terrestrial power grids. Architecting a space-based AI data center is an active optimization problem defined by known physics and hard economics.